Professor Jon Tunnicliffe. Great to have you here, Professor Jon. University of Auckland. One of the things that struck me about the bio of Dr. Jon was that he's worked at Niue in Christchurch and had lecturing position at Carleton University in Ottawa, Canada, before coming to Auckland. Jon has worked in a range of environments, from West Africa to Canada's far north to New Zealand's South Island. Really great to have you here to discuss with us today, Professor Jon, a sediment budget framework to support river management in Taihāwhiti. Kia ora. Mai te whakapāhi.
Thank you very much, everyone. It's a real pleasure to be here. This is just an exceptional gathering, and it's wonderful to hear all these many disciplines that are working on a common issue. That's great. Thank you so much. I could not ask for a better introduction to my talk than the two preceding speakers. Thank you for providing all of the background for my talk. I'd like to talk today about the sediment budget concept in terms of attempting to manage the cumulative impacts of all these landslips and earth slides and various processes at work in the catchments. This is, for those of you who have been newly introduced to geomorphology, this is our obsession. This is understanding all of the different linkages and the volumes of material that are moving through the system. And Ian's done a great job of underlining the importance of connectivity as we move between all of these different source areas, the linkages between the various transport corridors through the catchment and into the final storage zones and floodplains and the ocean system at the end of it. So I've been focused on the river aspects of it, mainly the Waiaku catchment is where I've been doing most of my work, although I've had a few projects at various sites throughout the East Coast. The river system has often been compared to, we can think of it as a sedimentary system as something of a flood wave moving through the catchment. Sediment moves much more slowly than water. So the model I have up here is something that was proposed. This is in the 1950s for a flood wave moving through a catchment. Sediment takes much, much longer rather than hours. We're talking about decades to centuries for gravel to work its way through the fluvial system. The gullies and all the source areas that we've been talking about are the tap at the top end that are supplying all of this material to the catchment. And as we move from the upper headwater catchments into the successively larger stream waters, we get into the signal transfers its way through the network, and we see a change in the wave of material that's moving from the headwaters down to the lower river. And so the reason for that change in that wave as it moves through the catchment is related to the sedimentology of the system, right? So the fine sediment tends to shoot out very quickly, whereas the gravels and cobbles tend to lag behind, and so we see a change in the form. Luckily, working in the East Coast, we have an exceptional data set of cross-sections, right? There's been monitoring in these rivers since the late 1950s, carried out by Gisborne Council. And this has assisted greatly in attempting to reconstruct the trajectory of the system over time. There's also a number of new technologies now coming online. Ian will show you some of the laser scanning technologies. So we're able to compare the modern configuration of the system with what we can reconstruct from the cross sections, and also using photogrammetry to reconstruct the historic imagery. We've got very high resolution scans now from the 1940s, 1950s, and we're getting much, much better at reconstructing that topography with reasonable accuracy. So once we have this old model, new scans of the topography now, we can difference those. And so this has commonly been done at the site scale, but we're looking at moving out into a much broader domain, trying to pick up how the landscape has changed in a very quantitative way over the last number of decades, since aerial photography has begun. This is just a quick case study of the Tekumi Gully. This is just, it's a tributary of the Rakokori catchment, just on the north side of the Waipu. As Ian showed you with the Tarndale topographic differencing over successive years, this is taking the air photo series from 1957, where there's almost no sign of this gully. It formed in the successive years, got bigger and bigger, and by using these photographic techniques, we can pick up the rate of evolution of the gully and work out the volumes that have come out and nail down some of the processes that are acting to propagate the gully and move material from the hill slopes to the fluvial system. You can see a cross-section here where it's eroding out the gully at the top and delivering sediment down to the river below. And there's quite a number of these gully systems that are, they have different pathways for moving the sediment from this weathered bedrock down to the river system. And so these coupling points are where we see complete changes in the river morphology, right? As we this system over here is showing the sediments coming into the river. The river goes from a narrow, meandering system to a broad, braided river system with multiple channels. It's an extremely dynamic river system. And so these coupling points are essential to building this wave model and trying to understand those connections between the hill slope and the broader river system. Another technique we've been using is drone-based structure from motion. And so structure from motion is a new photogrammetry methodology where, by taking a number of photos from drone-based platforms, with the overlap between those photos, we can use the 3D parallax effect between those photos to reconstruct the topography. And so we can move beyond simple cross-sections and start to look at how broader landforms are changing over time. Luckily, we have some LiDAR scans from 2006. This is from Earnslaw, who have scanned some of their holdings in the region. Having this topographic database, we're able to look at the modern system and speak quantitatively about how things have changed. It's not whether the extent of something has changed or just looking at the plan form or the cross-sections. We can look across the entire landform and look at how things have changed. So this is showing us 8 years of change at the base of this gully. And so this is from a publication that Mike Martin had demonstrated the effectiveness of replanting at the top of this is on the Ihungia River, one of the tributaries of Mata and the Waipu. And from this difference map, we can see the red is showing where it's eroded, right? So the supply of material from the gully is no longer filling up that fan anymore. It's cutting down, and we're starting to see a shutdown of that gully system following on from this sequence above. And with the structure for motion, we can also get at these process insights. So we can see the successive generations of material being shunted into the river system, and we can start to understand the processes at work at these coupling points between the gullies and the river system. A little further down in some of the larger rivers, we've been looking at the historic patterns of interaction between the main stem river and the tributaries coming in this case, the Tapawairoa. And so we've got 6 years of, 6 time slices since 1939. And it shows us how if we flick back and forth in time, how we've got these storage points, right? These intermediate points where material is being dropped off. And there's an interplay between that main stem river and that tributary. And so by elaborating these linkages, we can start to build these wave models and start to model how the system will behave into the future, depending on the scenario of slowing down these major sediment sources. This is a much larger exercise in the Tapawairoa River. This is using, again, structure for motion. This was a fixed-wing drone that flew along a 12-kilometer length of the river. This is just to give you a sense of the detail we can pull out of these models. And so this is the Raparapaririki River. Excuse my mangling of the local names here. Mike Martin had a great shot of this river in the process of burying a bridge. Right? So the old bridge is still under 4 or 5 meters of sediment. That's the new bridge. And if we zoom into this picture, you can see we're getting hundreds of points per square meter along 12 kilometers. So this is billions of points to represent that surface quite accurately. And the accuracy is within a few centimeters. So we flew the Tapawairoa in 2015 and again in 2016. And once we have two surfaces, we can subtract them and obtain a difference map. The reason we're so interested in this particular section is this is one of the critical, I would say the Raparapaririki is ground zero in terms of sediment supply to the larger system. We're starting to see it cut down in the upper reaches. That material is being shunted down into this first deposition zone down here. And so we're reaching this point where we think, if the current trajectory continues, we're going to see this tipping point where things are eroding at the top and shunting that material downstream. So we're going from cross sections to looking at the actual process that's happening. If we're just looking at a cross section, it's hard to know how the material is shifting, but we now have this longitudinal view of how the channel is moving material from one side to the other. This diagram is showing that 12-kilometer length. This upper blue chart is showing the gains and losses within each of the reaches. And so you can see some reaches are losing material, some are gaining. If we look at the cumulative picture over the length of the river, we can start to tease out where that accumulation is happening within the river, right? So we can actually capture that wave as it's moving down the fluvial system. So this is very exciting from a perspective of trying to model the transfer of this material through the river reach. And the other bonus is that we can see how that material is shifting, where the erosion is happening, whether the channel is widening, if it's coming from channel switching. So the reds and the blues are showing erosion and deposition. You can see how the fan at the Raparapaririki is being trimmed off by the Tapawairoa. So there's a really rich database of process information that we don't get from cross sections. And so it's very helpful from a management perspective to understand how the river is shunting material around and how these floodplain stores are changing along the length of the system. And so the next initiative, I suppose, is to look further downstream. So this is the Tapawairoa coming in from the north here. Is that right? Yeah, and that's the Mata. No, that's the Magaporo, sorry. A little further downstream. This is a 1939 picture of the lower Waipu. And if I flick between the years, you can see how the system has changed over time. The river is, on average, widened about 20%. So there's been no aggradation. But by switching back and forth, it has changed where it is storing sediment downstream. And based on what we understand about material moving from the upper part of the catchment, we're trying to understand now how it is going to shift into the lower part of the Waipu and how the incoming material relative to the capacity in the downstream channel is going to change. And I think that'll be a very enlightening exercise to do that sediment budget balance. Based on the cross-section, this is just showing a quick time series going from 1950 through to this vertical line of Cyclone Mola. This line with the 2006 attached to it is the accumulation within it's the relative rate of change based on the cross-sections in the Raparapaririki. So that crested in about 2006, right? So that's 18 years after Ebola came through. The next one, this dashed line, is the Tapawairoa. This gray line is the Tapawairoa on average, and down here is the lower Waipu. So you can see most of the action is happening in the upper catchment, right? So this is the excitation of the system. It's plateaued at the moment, starting to cut down in parts of the Tapawairoa. But what are the implications downstream, right? A lot of that material will eventually make its way downstream. Just by quick comparison, this is work done by researchers in California. Last name was James, I can't think of the first name. Looking at the effects of hydraulic modeling on the Sacramento River, right? And over the course of the mining of the riverbed, we saw a relatively dramatic increase in the aggregation. We're only looking at about 2 meters of aggregation as opposed to 30 meters. Some of the dramatic numbers in the water catchment. But the fact is, once the hydraulic mining, which was providing all the sediment that caused this disturbance, once it shut down, the system responded relatively promptly afterwards. It's a matter of decades. But nevertheless, the system does respond to that cutoff in the headwaters. So I think as we reach that critical point in the Waipu, when the gullies are no longer producing as much material, we could see a similar tapering of that wave moving through the system. So in conclusion, we're using this what's called a reservoir model, trying to route this material through the Waipu catchment and characterize the nature of these waves as they move through the system. Some catchments are still aggregating, building up their beds. Others are starting to cut down. So we're trying to do this mass balance to try and understand how the whole, the cumulative system will respond to various management approaches. And yeah, I think the sediment budget approach is helpful for understanding where interventions are most needed, how to prioritize which catchments need assistance, and where these points in the network are most sensitive and responsive to those management interventions. The important thing is having some sort of topographic benchmark, right? So this LiDAR scanning and structure for motion is quite helpful in terms of quantitatively understanding how the system is responding to these forcing effects. Thanks very much.